Hello my dear students, I welcome you to NEET World. So today we will be discussing NEET 2025, we have upcoming NEET 2025 examination, right? So for that I will be discussing completely from metal complexes, coordination compounds, right? So by using the previous year questions, so I will be revising the complete chapter here. Okay, so this will be definitely helpful for your upcoming exam. Okay, so what are the focused areas from this particular chapter? Just look at here. So first of all, based on the 2022-2024 papers, these many papers I have seen, the mostly questions are from, these are the topics we should focus. So questions are from mostly from these topics I have observed. So what they are exactly asking us? So in few questions they are asking about coordination number and oxidation states. Anyways, in order to understand the other remaining topics, we need to identify coordination number and oxidation state. This is a very basic thing first. Okay, so once after completing this from the metal complexes, then we need to know the electronic configuration of the metal in that metal complex. So they will be giving some metal complexes and they will asking us to find the oxidation state and also the electronic configuration of the metal atom which is present in that complex. Okay, and how it will be affected when we have different ligands. So there is a concept called strong field ligand and weak field ligand. So how this electronic configuration varies when we have strong field ligand and when we have weak field ligand. So this is also important thing. Then next, some important theories we need to study here. So what are the important theories? We have Werner's theory, and the next Sidgwick EAN rule, right? Effective atomic number, finding effective atomic number of the central metal atom in the given complex. That is also the second thing. And the next what? Valency bond theory, VBT we are saying. And the next third one is crystal field theory, that is what? CFT. So these are the things we need to focus here. Okay. Then next, in crystal field theory, we will be studying about ligand field strength. Yes or no? Ligand field strength based on the spectrochemical series, the chemical spectral series. So based on the experimental data, we will be having the ligands which are strong field and which are weak field, and they are arranged based on their field strength, right? So that order is also one of the very important point and important thing to remember, because they directly ask based on the order, or they will be giving in some complexes which are the following complex will be having inner orbital complex, like whether the based depending upon the ligand, we need to decide whether it will be having paramagnetic nature or diamagnetic nature. That is also we need to understand here, or whether it is forming inner orbital complex or outer orbital complex. Yes. Then next, geometry and magnetic nature. So geometry, so in order to find geometry, we need to know its hybridization. So valency bond theory is also very important thing. And then next, the magnetic nature, whether it is diamagnetic, paramagnetic. For example, they will be giving a complex like this, nickel tetra coordinated complex. Here it is, here we have carbonyl ligand, and sometimes they will be giving same nickel Cl4 times chlorine 4 times Cl4 with -2, and one more complex they will be giving nickel Cn4 times cyanide 4 times. So these are the tetra coordinated complex of nickel. So what is the hybridization of nickel in all these three complexes, and what is the magnetic nature, whether it is diamagnetic, paramagnetic, or what exactly, they will be asking for this kind of ligands. And these three ligands, three complexes are very important. Okay, we need to get some clarity on these three complexes. Okay, and the next, isomerism, structural isomerism and also stereoisomerism. Like structural isomerism, again we have now ionization isomerism, solvate isomerism, and linkage isomerism, coordination isomerism. These things we need to focus from this particular chapter. Yes, so these are the main important things to be focused now, and we will be revising all these things using the previous year questions of NEET. Okay, so I suggest you to focus into the class and you can take the notes. Okay, so generally let us start the topic from very basic. So generally like inorganic compounds, let us say molecular compounds, are divided into two types. One is double salts, another one is coordination compounds. So what exactly this double salts? See, I think we are well aware of this Morse salt, right? So what is a Morse salt formula? See, Morse salt we will be seeing, potash alum we will be seeing, all this comes under salts. Okay, so let us say this Morse salt having ferrous sulfate and ammonium sulfate formula. So ferrous sulfate FeSO4 and ammonium sulfate dot 6H2O. So this is what more salt. So upon placing this in the aqueous medium, what happens to the salt? What happens to the salt? It will dissociates into its ions. It means this salt loses its identity when we are keeping in the water. So when we are placed in the water, aqueous medium, it loses its identity. So these are for double salts. Okay. Now when we take any coordination complex, when we take any coordination metal complex, so what happens? It won't lose its identity when we place in the aqueous medium. So the properties will remain same even after placing in the water, but normal salts, they loses their identity. For example, here we have copper tetra coordinated complex and here we have iron hexa coordinated complex. So these complexes, when we place in the water, see, they just getting ionized. What we are seeing here, see, this whatever the 4 coordination, like 4 metal atoms are there, like 4 potassium atoms are there, ions they just got dissociated like 4 K plus, and the remaining this coordination sphere remains same. It means whatever the ligands which are present along with this metal in this coordination sphere. So this is what the square bracket represent coordination sphere in the metal complexes. Okay. So whatever the elements present inside this coordination sphere remains same. They won't involve in this dissociation. They just remains as it is. Therefore the identity will not be lost by this metal complexes. The identity of this metal complex remains same even after placing in the aqueous medium. Okay, I hope it is the basic difference is clear between the salt and a coordination compound. Okay, so these coordination compounds are highly stable. So generally how these coordinated complexes are shown? So generally we will be using a square bracket, okay, in which metal atom is represented with M. Let us say M is a metal atom, metal present in that coordination compound or coordination complex, okay, and there will be some ligands. Okay, so L represents ligands, okay, around this metal atom, surrounded around this metal atom, and let us say n number of ligands are there. Okay, so this n represents what? Number of ligands in this metal complex. Okay, now here if this complex contains any charge, that charge will be represented here. So plus or minus x represents what? So plus or minus x represents, give me a minute, there is some blurriness. So I think still it is there. Let me check here. So now what I am saying, so M is a metal and L is a ligands. So N represents number of ligands surrounded around this metal atom. Okay, so what is this X represents here? X represents charge present on this metal complex. Okay, I hope it is clear. So here the number of ligands around the central atom or number of ligands binded around this central atom will be called as its coordination number. Okay, so for example I am writing a complex here. So cobalt, metal atom here is cobalt, and hexaamine complex I am writing NH3 6 times. Okay, so here I am writing chlorine. So 3 ions I am like 3 chloride ions I am writing like this. So here how many ligands are there? So ligands are, see, NH3 is a 1 unit. Okay, so each NH3 will be having a pair of electrons like this now. Okay, and here metal atom is there cobalt. Okay, so this ligand, by, see, we know metals are electropositive, therefore so it will be having some positive charge here based depending upon the negatively charged ligands. So oxidation state will be determined. I will explain about oxidation state. Okay, to that metal atom this ligand will donate a pair of electrons. Okay, so that's how the complex is formed here. So how many ligands are there here? 6. Therefore we should say coordination number of this complex as 6. I hope it is clear. Okay, now we should not consider these as a ligands here. Okay, because these are outside the coordination sphere. So whatever present inside the square bracket, the square bracket is called coordination sphere. Coordination sphere. Okay, so these whatever the species, like here chloride ions are there 3. So these are ionic sphere. They are not inside the inside the coordination sphere. Therefore these are not considered as ligands. Only the species, only the ligands, only the species which present inside the square bracket along with this metal are considered to be ligands. I hope it is clear. Okay. Now if this ligand is having no charge, see ammonia is a neutral ligand, there is no charge, so I can say this ligand as a neutral ligand. Okay. The charge with respect to this ligand will be considered to be 0. I hope it is clear. Now there are one more type of ligand, there can be charged ligands. So generally ligands are of two types, one is neutral ligand, another one is negatively charged ligand. For example, halogens will be having negative charge. So for example, here I am writing chloride ion. Okay, if this chloride ion present inside the square bracket, I can consider this as a ligand. Okay, now here chloride ions are present but not inside the this square bracket, so these are not ligand, these are not ligands, they are just ions. So if we place this in the water, what happens? So in the aqueous medium, the square bracket part will remains same. So NH3 6 times plus 3. Okay. Now why I am writing plus 3 on the square bracket? Because these 3 ions will get dissociated and it will form 3 chloride ions. So this is how you need to understand the concept of this coordination compounds. Okay. So now here one thing you need to remember, so what is the oxidation state of this metal? So let us say for this metal atom I am writing it as X. We need to find the charge, the oxidation state of this metal atom, which is considered to be X. Now I told you ammonia is a neutral ligand, so how many are there? 6 are there. So if it is neutral, the charge with respect to that ligand will be 0. Okay, and equals to I am writing. So why I am writing equals to? So if we take like this, if the charge is present on the coordination sphere, so just write it as equals to that charge. If you consider here there is no charge now, so whenever we have no charge on this, so you can do in this manner, both are correct only. I will be telling you both models. So here X, 6 ligands are there, 6 into charge of each ligand is 0 plus how many chlorines are there outside the sphere? 3. Okay, what is the charge of each chloride ion? So -1. Overall molecule is neutral, so it is equals to 0. Okay, if it is charged, right, it is equals to that particular charge. So X will be how much now? See, this will be -3, if it goes that side it will be +3. So this is the oxidation state of the metal in this coordination sphere. I hope it is clear. Now here also if you calculate, you will get the same oxidation state. Let us say this is X plus 6 ammonia ligands are there, each one is charge is 0 and equals to what is the charge present on the sphere, on complete coordination sphere, it is +3. So X will be +3. So this is how you need to calculate the oxidation states. I hope it is clear, there is no confusion, right? Okay. So let us move forward for more clarity. See, sometimes there will be different ligands. For example, there is something called bidentate ligand. So here for ammonia only one dentating site, it means only one binding site is there for ammonia towards the metal, right? Sometimes there are some ligands, they can bind from 2 sides. For example, ethylene diamine. So what I am saying, ethylene diamine. Okay, so cobalt. So here I am writing ene 2 times, it's Cl2. So what exactly it is saying here? Look here, so ene means ethylene diamine. So you should write the structure like this, CH2, NH2, NH2. So this is the ethylene diamine. Okay, so here ethylene diamine, cobalt we have now. So here in the cobalt it will be +3 oxidation state in this case. Okay, so now how many ligands are there here? So ene means this is the structure of ene. So you should say it as ethylene diamines. Okay, so this is one dentating site and this is another dentating site. So one ethylene diamine having 2 dentating sites, right? So we should say the ligand as bidentate ligand. Okay, what is that? Bidentate ligand. If it is having 3 sides, we should say tridentate. If it is having 4, tetradentate, pentadentate, hexadentate. So let us say them as polydentate. Okay, I hope it is clear. Okay, so ene is what? Ethylene diamine, which is a bidentate ligand. So therefore, what is the coordination number of this cobalt in this complex, they will ask. So for each in, it means for each ethylene diamine there are two dentating sites. It means with respect to one in, there is coordination number is 2. Like that we have 2 ins now, so 2 plus 2, and how many chlorines are there? So 2 chlorines, each one will be having one dentation, therefore so it will be monodentate ligand. So I can say 2 into 1, so therefore how many dentating sites? Coordination number will be 6. So this is how you need to understand the basic concept of this coordination number and oxidation number finding. Okay, I hope it is clear, right? Okay, so whenever we have monodentate ligands only, if all the ligands attached are monodentate ligand, so you just take coordination number equals to number of monodentate ligands, If here if we have bidentate ligands, bi means 2 na, so 2 into number of bidentate ligands we have to write. If we have tridentate ligand, so 3 into number of tridentate ligands. So here how many we have bidentate ligands? 2 bidentate and 2 monodentate. So what is the coordination number formula? Here we can get coordination number equals to, so number of bidentate ligands are 2, so 2 into, so since I am saying bidentate, so 2 into 2, right? Number of monodentate ligands are 2, so mono means only one dentating site is there, so 2 into 1. So overall how much? 2 to the 4 plus 2, so total 6. This is how you can make the formula. So I hope it is clear, right? Okay, how to find the coordination number? Number of monodentate ligands into 1, if it is bidentate, so number of bidentate ligands into 2, if it is tridentate, number of tridentate ligands into 3, like that we should write. I hope it is clear. Finding the coordination number is done. Now, is there any charge on this in? Ethylene diamine have no charge, so I can say neutral ligand. But chlorine will be having Cl minus, right? Okay, so each chlorine will be -1. There are 2 chloride ions, therefore it will be -2. So what we can do here is, so let us say for cobalt here, in this case, let us say this is X for cobalt, and in ethylene diamine 2 are there, but each one will be having 0 charge, plus, and the next how many chloride ions are there? 2 are there, so each one will be with -1 charge. Overall molecule is having charge as +1, so equals to +1. So therefore what is the X value? +1. So if it moves that side, so it will be +3. So I hope it is clear. So what is the coordinate? What is the oxidation state of this cobalt here? So oxidation state of cobalt in this case is +3. Coordination number is 6. I hope it is clear. So they will be definitely giving a question like this. So find the oxidation number and the coordination number of this given complexes, or match the following complexes with respect to their oxidation numbers and coordination numbers. So this kind of questions you may expect in the exam. So now tell me for this coordination number of platinum in this complex. What is the complex given? So Pt NH3 4 Cl2 plus 2. So this is the complex given. So tell me what is the coordination number? How many ammonia ligands are there? 4. We know ammonia ligands are neutral ligands now. So 4 into neutral and monodentate, 4 into 1. Okay, plus chlorine ligands are also monodentate. How many are there? 2. 2 into 1. So total coordination number is how much now? 4 plus 2. So it is 6. That's it. This is the coordination number. So now I will be asking you to calculate its oxidation state. What is the oxidation state? So for this particular question we already got the answer, that is 6. That is done. So my question in the comment box, you need to answer for this oxidation state of this particular complex. Write it in the comment box. So let us take this as hashtag question number 1 and write the answer for that particular question. Okay, so just I want to check how many of you are there here. Okay, so let us move further. Oxidation state of iron in this particular complex. Okay, so what is the oxidation state here? So we have 2 types of ligands here, CN and next one is NOS. Okay, so here just look into this thing. So I will be showing you one basic thing. So types of ligands, you can just look here. So denticity means see what I told you, the number of lone pair electrons donated by a ligand. So for H2O, one lone pair is donated, the denticity is 1. I can say water molecule as a monodentate, ligand. Okay, so monodentate ligand I can call, or otherwise I can call unidentate ligand. Okay, monodentate or unidentate. If it is having two dentating sites, bidentate. If it is having more than 2, I mean 3, 4, 5, 6 like that, we should say it as polydentate ligand. Okay, so here monodentate ligands can be neutral again, it can be negatively charged. Okay, so neutral ligands I can say water and I can say ammonia. All this comes under what? All this comes under what? Neutral monodentate or unidentate ligands. They can only form one bond with the metals like ammonia, alcohols, ROH. So these things comes under what? Monodentate ligands. Okay, so there are some monodentate but negatively charged ligands. These are neutral, these are negatively, Cr minus, Br minus, Sn minus, something like this. They are negatively charged ligands. Okay, here CO, carbonyl group also the monodentate ligand here. Okay, so there are something called bidentate ligand. I told you ethylene diamine. So ethylene diamine will be having, so ethylene CH2 group, here NH2, and this side also NH2. I told you this already. Okay, oxalato. So we know oxalic acid formula will be there now. So what is the formula of oxalic acid here? So you just write CH2 like this, CO, O minus, H2C2O4 is a oxalic acid formula. So I am saying oxalato. Oxalato means the negatively charged 2 oxygen atoms will be the donors here. So if we have a metal here, so towards that the negatively charged like oxygen atoms will donate their lone pair electrons, I mean pair of electrons from each of the oxygen and make a bond with this central metal atom. See now how many dentating sites are there in this ligand? 2 dentating sites. So I can say oxalato is a bidentate ligand with a negative charge. So negatively charged bidentate ligand. So what are the donor atoms in this oxalato? It is OO donor. So 2 oxygen atoms only donor na. So bidentate, we should say bidentate OO donor. So that's how you need to answer. Okay, that is also important. Which are the donating sites? So in ethylene diamine, what are the donor sites? So you should say ethylene diamine, we can say it as bidentate neutral ligand and having N donor sites. What are the donor sites? N and N, nitrogen are the donor sites. So this is what the ligands here. Okay, next ambidentate ligands, one of the important thing here. Ambidentate means, see we know ambidextrous means the person can write with both hands, right? So ambidentate means, so he can, I mean that ligand can bind to the metal or dentate to the metal to this side or also from this side. Okay, so it can be possible from the both ends. So for example, SCN is there now, so here it can donate from this sulfur side or it can donate the electrons from nitrogen side. So this is what the this ambidentate ligand. For example, even cyanide if we take, so it can donate from the nitrogen side or it can donate from the carbon side. Okay, so this, what are these? So these are bidentate ligands, ambidentate ligands. What are those? Ambidentate ligands. Okay, so if a ligand has 2 dentating sites, I mean from the any of these ends, so that I can call it as ambidentate ligand. Okay, so one of the important thing. So now tell me, can I call oxalate as bidentate ligand? No, because it is having only one kind of dentating site, that is oxygen minus, here also oxygen minus. Oh, okay, so other than this there is no other sites to bind with the metal, right? Okay, so this is bidentate ligand but not the ambidentate ligand. I hope it is clear. There is a question on this, we will be looking into it. So the next polydentate. So out of this all polydentate ligands, we have a important question here is, so ethylene like EDTA we have seen na, EDTA. So what exactly it is? So ethylene diamine tetraacetate. So CH2 CO O minus, so CH2, so acetic acid group here we have acetate, so this side 2 and this side 2. So I can write it has negative. So one of the very important and commonly asked question. So this is the structure of EDTA. So here maximum number of dentating sites for this EDTA is, so what I am saying, ethylene diamine tetraacetate. So it means if it is having negative charge on all these acetate groups, acetic acid groups, so we can say this is acetate, tetraacetate. So now how many ligating sites are there? 4 oxygen atoms. This negatively charged oxygen atoms can be donate a pair of electrons to the central metal atom. So it can be tetradentate from the outside, and from this nitrogen this can also donate, this can also donate. So totally how many dentating sites? 1, 2, 3, 4, 5, 6. So there are 6 dentating sites for EDTA. So maximum EDTA can form 6 bonds, 6 dentating sites are there. So I can say hexadentate. EDTA is a hexadentate ligand. So what are the donating site, donor atoms here? So 4 are oxygen atoms and 2 are nitrogen atoms. So this is also one of the important question and previously asked question. Look here, which are following is not an ambidentate ligand? Yes. So identify. So here SCN minus is there. It can donate from this side or from this side. Okay. So I can say this is ambidentate. For nitro group here NO minus and here like this. So it can bind from this nitrogen side or it can bind from this oxygen side. So if it is binding from this side, I can say N atom, nitrogen atom is donor. So this is one donor, and if it is binding from here, I can say O donor. So it means 2 donating sites are there. So I can say this complex, this ligand as a what? Ambidentate ligand. Okay, from even from cyanide also it is possible, from SCN also it is possible, but not from the oxalate. Okay, we already discussed, right? Okay, so option for that is first one. Okay, so these are very fresh questions, last year questions only. Ethylene diamine tetraacetate ion is what? Just now we discussed, it is a hexadentate ligand with 4 O donor, 4 oxygen atoms and 2 nitrogen atoms act as a donor sites, right? So fourth option is perfect answer for this question. And then next, ethylene diamine tetraacetate ion is an, see, 2021 again 2024. So this is a frequently asked question. See, ethylene diamine tetraacetate ion is an what? Hexadentate ligand. That's it. Okay, we will come back to these theories again. So is there anything we missed? Yes, finding the oxidation states here. So now look here. So cyanide is SCN minus, so negatively charged, mononegative, and NOS is also negatively charged. Okay, so now here I am asking for iron. So the given complex is what? The given complex is Na4 FeCN NOS. Okay, and that's it. This is 5 times. So let us take this as X for iron and 5 nitrogens. Okay, 5 cyanides, so 5 each one with minus 1 charge. Okay, plus NOS, this is also a ligand, negatively charged ligand. So 1 into minus 1 equals to, so what I can make? So I can make equals to 0. In order to make equals to 0, so here I am adding plus. So how many sodium atoms are there? 4 sodium atoms. So 4 into 1 plus 1 for each sodium alkali metal. Therefore overall charge will be, overall metal complex is what? Neutral. So equals to 0 I am writing here. 0 I have made here. Okay, now tell me. So X can be, so minus 5 minus 1. So can you say minus 6 and plus 4. So that will be minus 2 equals to 0. X can be plus 2. So this is the oxidation state of iron Fe in this particular metal complex. So you can write Fe plus 2. It's the charge of this metal complex. Oxidation state of this metal atom in this complex. I hope it is clear. So we can go with option number 2 for this particular question. Now next, which are the following will exhibit maximum ionic conductivity? Yes, one of the easy and important questions. See, so basically what I told you, when a metal complex is placed in the aqueous medium, so the outer sphere ligand, so other than the coordination sphere, whatever the atoms are there out of the coordination sphere, that will get ionized, right? Okay, so more the number of ions, more is its ionic conductivity. See now here K4 FeCN6 is there. So it means after ionization, when we place this in the aqueous medium, it will give 4 potassium ions and 1 FeCN6 minus 4. So these are the these are the ions we can expect. So 4 potassium ions and 1 complex ion. So total ions are 5. Like this, count the number of ions possible. For this is 1, this is 2. So totally 3. For this, these are 3 are there, this is 1. Overall 4. So which is having more the number of ions? So more the number of ions are for 1. Therefore it will be having maximum conductivity. So you can choose option number 1. Like that, even we can arrange them in the order also. More the number of ions, more is the conductivity. Then 1, 2, 3, 4 is the answer. So 1 is having maximum conductivity, right? I hope it is clear. Now I told you the complex gives test for which of this species. See, I told you it won't lose the identity. Metal complex won't lose the identity, or the whatever the ions present inside the square bracket, that coordination sphere will remains in that. They won't come out. They remains as fixed, and only the ions or the species which are outside the coordination sphere become ions, and that can be loses their identity, or they can react with others. But the whatever the ligands present inside the coordination sphere won't come out here, okay, in the aqueous medium. Therefore this chloride ion will be evolved here from this. So we can say this test, the test gives for chloride ion only, okay, not for the other ions. I hope it is clear. Next, these things we discussed. Done. Just have a look into this question. If you are already aware of this, just give a try. I will be taking some water. So before that, look into these 2 questions. Identify the homoleptic complex. Yes, identify the homoleptic complex. So what do we mean by homoleptic and heteroleptic? So homoleptic means all the ligands present inside the coordination sphere should be same. For example, I have a metal complex like this. So complex should be written in a square bracket, like square bracket represent the coordination sphere, in which we have a metal here M. Okay, so along with this metal, so all the ligands which are attached to this metal in this sphere should be same. So all should be if it is hexa-coordinated complexes, so it should be 6 ligands should be same type. It means, for example, we have let us say manganese complex here. So if it is having +2 or whatever the oxidation state here, so here manganese I am writing. So all the ligands which are present inside, it should be of one type, like MnH2O6, or it can be MnH2O, it can be Mn ammonia, or whatever it can be. It can be MnCl6, like this. And these 2 are what? Now these 2 complexes, whatever the charge, here I am writing +2 here, okay, here I am writing -4, okay. So these 2 complexes are what? Homoleptic, because all the ligands present inside the sphere are same. Okay. Now if I make something like this, MnCl3 H2O3. So this kind of ligand, if we have this kind of complex, if we have, then I can say this is what? 2 different ligands are there, na? H2O 3 times. Okay. So this kind of ligand complexes are there means, so this can be considered as heteroleptic. It means more than one type of ligand is present inside the coordination sphere, can be considered as heteroleptic. If all of them are same, homoleptic. I hope it is clear. Now tell me, identify from this explanation, you try to identify from the 4 options which is homoleptic. All the ligands attached should be same. Okay. So this comes from, see, diamine, dichlorido, diamine, chlorido, nitrito. It means 3 different ligands are there. So this is not homoleptic. Okay. Pentaamine, that is fine. Carbonato, see, again 2. this is one type, this is another ligand. So two different ligands are there, so I can say it is also heterolyptic but not homolyptic. So here triamine, triaqua, chromium, so two different ligands are there, this is also heterolyptic not homolyptic. And what about this potassium, right, potassium, okay. Then next trioxalato, so in the short form let us write ox, okay. Tri means 3, okay. Aluminate like this, so you can put these 3. See, only one type of ligand is there now, oxalato ligands are there inside the sphere. So it means if only it contains one type of ligands, we can say they must only one ligand multiple times, we can say it as homolyptic. So which is the suitable answer? Fourth option is the correct for this particular question. I hope it is clear, right? Then next come to this Werner theory. Let us start our theory discussions. Okay, so Werner theory, what he explained here, so ligands will satisfy, like around the metal atom ligands are surrounds, okay. So now, so these ligands can be of two types, one is negatively charged, one is neutral ligands now. So here when it comes to this Werner theory, so he told there are two types of valencies, one is what, secondary valency, other one is primary valency, okay. So this primary valency is satisfied by negatively charged ligands. Which ligands? Negatively charged ligands. And we can say primary valency is also equals to its oxidation state of central metal in the particular given complex. Secondary valency is can be satisfied by both negatively charged ligands and also neutral ligands. Therefore secondary valency can be equals to coordination number in that in the given complex, okay. Now Werner does not given proper reason or proper explanation about the nature of bond, okay. So I can say ligands, this ions by covalent bond, he was not explained about this type of bonds between the ligand and the metal in his theory, okay. Later in the other theories it was given, okay, about the bonds, type of bonds, okay. Secondary valencies have directional properties, yes. So they have directional properties now, because around the metal atom they will be coming in particular, they will be oriented in a particular direction, therefore it will be having some hexa coordinated complex, I am saying. So it means that ligands will be coming from a particular direction, therefore it is giving its geometry also, right. Okay. So now what I can say, secondary valencies have directional properties, yes, and the secondary valencies are non-ionizable, okay. Then next, secondary valencies are satisfied by both, yes, here I told now secondary valency, which is coordination number, can be valenced by both neutral as well as negatively charged. So out of these 3 I can go with 2, 3, 4 are correct, 2, 3, 4 are the correct statement but not the first statement. I hope it is clear. So this is about Werner theory, okay. So one thing you can remember, what is the primary valency? That is nothing but the oxidation state. Secondary valency is coordination number. Here I just wanted to add one more question here. For this particular ligand, particular complex, so tell me what is the otherwise let us say Cl3. For this particular complex, you tell me what is the coordination number and oxidation number, or they will ask, instead of like this they will ask what is the primary and secondary valency of this complex, they will ask. So what I told you, just find the oxidation state, that will be equals to the primary valency. So here we know ammonia is neutral ligand, therefore what, and chlorine is negatively charged ligand, and then consider X 3 into 0 plus 3 into minus 1 for each chlorine, overall molecule, overall complex is neutral, therefore it is equals to 0. So I can say X is equals to plus 3, okay. So it means primary valency is what, equals to oxidation number. So primary valency for this is 3, okay, oxidation number. Secondary valency is how many ligands are there here, 3 and 3. So 6 ligands are there, which is hexa coordinated complex. So I can say it is hexa coordinated complex, therefore secondary valency, which is equals to coordination number, is 6. Like this you need to answer. I hope it is clear, no confusions, right. Next, writing the IUPAC name also one of the important thing here in metal complexes. So in order to write the IUPAC name, you should also know what type of ligands they are, and also finding the oxidation state also important thing, because we need to write the oxidation state also. So there are some basic rules. I just want to give a quick revise using this question. See, whenever we are writing the name for a particular complex, first write the name of ligands, then write the name of metal in the complex and represent its oxidation state in a parenthesis, okay, like this, okay. Now one more thing, so whenever we are saying some inorganic compounds, let us say I am saying the salt NaCl, which is sodium chloride. So first of all we are writing for the cation name and then followed by anion name, sodium chloride, right. Here also follow the same trick, okay. So here we have two parts, this is one part and this is another part. So there are two spheres. So first one is cationic position and another one is anionic position, like sodium cation, anion is chloride, like that, no. So write the name first for cationic sphere, then for anionic sphere, because we are saying sodium chloride, similar to that, okay. Tell me, so here we need to write, so what I can write, okay. So first in the given coordination sphere, first give the name for ligands. So what are the ligands we have? Water ligands. For water we can say aqua. How many are there? 2 are there. So diaqua. Here silver, when it is in the cationic position you should say it as silver, when it is in anionic position you should say argentate, okay. Silver, diaqua, silver, okay. So we will write the oxidation state later, so just keep it aside like this in the parenthesis, okay. Because if we consider only this first sphere, aqua molecules are neutral, therefore oxidation state for this will be 0. But whenever we have multiple coordination spheres, we need to check the most stable oxidation state for the given metal atom, okay. So for here cyanide ligands are there, each one is -1 charge, 2 are there, therefore in this complex we will be getting the charge as +2 for the metal atoms, right. But here also silver, here also silver, therefore in the both cases here we will be taking +1, here also we will be taking +1, because +1 is the most stable oxidation state for this silver. I hope it is clear. Now diaqua silver, in the bracket write 1 for this one, it is over, and now leave a space, some space here, and write for this one. So dicyano, okay, dicyano, okay. So for anions, we should, anionic ligands we should write cyanido, or ido should be, if it is chlorine we should say Cl minus chlorido, like that. So cyanido, okay. Sometimes they will also mention cyano, that is also fine, okay. If there is no cyanido you can go with cyano, okay. So cyanido. Next for silver we should write dicyano argentate. What is the oxidation state? Here I told you if we do for this separately we will get +2, but what I told you, they will share the oxidation state, overall molecule become neutral and stabilized. So here also 1, okay. So what is the option we have? Like this, see here we have diaqua silver, yes, diaqua silver, 1 space, then next dicyanido argentate 1, yes. Option 3 will be the most correct answer for this question. I hope it is clear. Homoleptic done. Here also all 6 ligands are same, it is a homoleptic complex, whereas these are having 2 different ligands, ammonia and chlorine, so heteroleptic ligand. So this is statement 1 is correct, and second statement is complex has only one kind of ligands, but it having more than one kind of ligand. So I can say this second statement and first statement both are correct. So statement 1, 2 both are true. Okay, see already we have solved this question in 2024 paper discussion. NEET 2024 paper discussion is already done. So from 2019 to 2024 I have discussed all the PYQs of chemistry part, right. So you can go through the playlist or you can go through the live session. So just click on the live button in the channel and you can see the like videos. So whatever the year question you want, you can go through that and you can watch that, okay. So you can even go through botany, zoology also, okay. So everything is discussed very clearly, Okay, so first prefer to the chemistry part, then go through the other subjects too. Okay, now look here, how can we match these two things? See what exactly this linkage isomerism, ionization isomerism, coordination. See, whenever you are seeing the coordination isomerism, so one thing you should get into your mind is there should be two coordinations pair, only that type of complexes will show coordination isomerism. Done. With that point, see, only in this option we have two coordinations pair, so only by exchanging the ligands from here to here, from here to here, we will get different coordinations pair isomers. Therefore, I can say C4. So C4 is there for how many options? C4, C4, only these two options we can expect now. 1 and 4 you can eliminate. Done. Now see, one more thing here, see, here water molecules are there now. So now by exchanging this chlorine inside and water outside, so water is a solvent generally, aqueous medium. So therefore, so D shows what? Solvate isomerism. So D1, how many of them are having? Only option 2 is having D1. That's it, done with the question. So 4, C4 I told you, done, and D1, that's it. So we got the second option. Okay, so by looking to the other options also, here ionization isomerism means upon ionization the compounds will release different ions, but they have same molecular formula. For example, in this case, now if we ionize this complex, we will get bromide ion as a ion. Okay, now if we exchange this bromide inside, sulfate outside, in that case we will get sulfate ion as a ion. So we are getting two different ions now for the same molecular formula containing compounds. So therefore, B is considered to be ionization isomerism, shows ionization isomerism. So B3. Okay, now A2, because A2, yeah. So nitro, like I told you, it can bind with this oxygen on this side, it can be binding with this nitrogen side. So the different linkages are possible now. So it can be N donor site or it can be O donor site. So this kind of like complexes which contain ambidentate ligand can show what? Linkage isomerism. Complexes which contains ambidentate ligand shows linkage isomerism. I hope it is clear. Okay. So that's why option number 2 is most appropriate answer for this particular question. Now, in order to understand the metal, geometry and all, we need to know this thing, spectrochemical series, where we will be studying it in the CFT, crystal field theory. Okay, so now these are considered to be weak field ligands. The strength is increasing as we moving this side. Okay, now EDTA is considered to be strong field from here to here. See, this side from up to here, this is a strong field. So CO is a strong field ligand. CO, carbonyl is a strong field ligand. Okay, so always remember this in the simple manner. So C donors are strong field ligands, then the N donors, then the O donors and halides. So generally halides are always weak field only. Here they can be weak field ligands when and C donors are very strong field ligand. That's why cyanide, CO are showing very strength. Okay. This order is also important. If possible, take a screenshot for your reference. Okay, and one more thing. Now these strong field ligands will be having more splitting ability. I will show you. Okay, more splitting ability, and they will form inner orbital complexes, whereas weak field ligand forms outer orbital complex. Okay, I will show you about that. And one more thing, most of the polydentate ligands will be act as strong field ligands. Okay, this is a general what you can remember. Okay, now in order to find the hybridization of nickel here, okay, we need to use the concept VBT, valency bond theory. First thing is write the given complex. Done, written. Then next, identify the oxidation state of nickel in this complex. So it will be having, see, let us say this is X. For metal atom it is X, let us consider. Okay, now we need to find the X value here. So cyanide ions are 4 are there, so each one with -1 charge. And what is the metal complex is having charge which is equals to -2, like this you can make. Okay, X can be now -2, this +4, so it can be +2. So nickel is having what is the charge now? Oxidation state is +2. I hope it is clear. Now we know nickel atomic number is 28. So now write the electronic configuration in this manner. If it is 28, just write 3d8 and 4s2. Okay, this is in its atomic form. Okay, now in its ionic form +2 oxidation state. So remove electron, 2 electrons from the highest energy level. So 4s electrons we can remove, so that we can get 3d8 4s0. So this is the electronic configuration of this nickel in this particular complex, right? Now these d orbitals, write it in this format: 1 2 3 4 5. 5 d orbitals are there. Second, third, fourth, fifth, sixth, seventh, eighth electron is done. Okay. Now how many ligands are there here? 4 tetra ligands, tetra coordinated complex, 4 ligands are there. So this is 4s. After 4s we have 4p0 orbital, right? So write that also. Okay, write the 4p also. Okay. Now look here. Here we have cyanide ligand, na? So we need to know what is the nature of that ligand. So from this story, I told you cyanide ion is a strong field ligand, na? Therefore cyanide ion is cyanide SCN minus is strong field ligand. You should get this clarity while doing the question itself. Okay. Now whenever we have strong field, so this strong field, it will pair up the unpaired electrons if any empty orbital is arising from that. So if it is pairing up, so we will be having something like this. So write all the electrons, remaining electrons, 8 electrons is done. Okay, now we got, after pairing these 2 electrons, we got an empty orbital here, and remaining we have 1s3p. Okay, now how many empty orbital, how many ligands are there? 4 now. So it means each ligand will donate pair of electron. So Cn minus, so here 1 and here 1, here 1, here 1. So how many orbitals are utilized here? What are the orbitals utilized here? 1d, 1s and 2p. So I can write d, s, p, 2 hybridization. So this is a hybridization of this complex. I hope it is clear with simple manner. Right? Is there any unpaired electrons here? No unpaired electrons. So mu value will be 0, and I can say it is a diamagnetic and magnetic nature is diamagnetic and movement will be 0. I hope it is clear. Spin only magnetic movement value is 0. I hope it is clear, no confusion, right? So now my question is this one. So try to answer for this NiCl4 2 minus. So here we got sp2 hybridization now. So whenever we have sp2 hybridization, so geometry will be square planar. What is the geometry? Square planar. Okay. Now for this, if we do, so here also nickel will be having +2 oxidation state. Okay, it means 3d8 4s2 4s +2 now, so 4s0 4p also 0. So Cl minus, what kind of ligand I told you? It is a weak field ligand. All halogens are weak field ligands. Okay. Now what is the electronic configuration? Just fill in the orbital boxes. 1 2 3 4 5 6 7 8 done. Next 4s 4p. Okay, done. Up to here it is fine. Now I told you that chloride ion is a weak field ligand, so it cannot enhance the pairing, right? So electrons will be remains as such. Therefore only the chloride ions will donate the electrons to the other empty orbitals, but it won't alter the electronic configuration. It remains as in the free metal. But whenever we have strong field ligand, so if the possibility is there for pairing, yes, so it will pair up the energy. Okay, when it is possible, pairing takes place in presence of strong field ligands. So we can also remember one thing. So always the magnetic moment for weak field ligand containing complex is greater than the strong field containing complex. I mean for a particular metal in the same oxidation state. Okay. Now for nickel +2 +2, here we have weak field ligand, here we have strong field ligand, therefore all the electrons are paired here, but here it is not paired. So what are the orbitals used here? One s, remaining are 3 p's, so sp3 hybridization, therefore if it is sp3 we know geometry will be tetrahedral. Here it is dsp2, geometry is square planar. Now what about magnetic moment? How many unpaired electrons are there? 2. So magnetic moment you can calculate root over n into n plus 2 Bohr magneton. So by using this you can calculate. So you will get the n value put here, you will get the magnetic moment value, and since it is having 2 unpaired electrons we can say it is paramagnetic. Okay. So now I have a question for you. So you have to do it in the comment box. So I am writing hashtag question number 2. Tell me hybridization and paramagnetic or diamagnetic in the comment box. So I am writing it as CO, cobalt, not cobalt, this is carbonyl. Carbonyl is a strong field ligand 4 times, and it is a neutral cobalt, not cobalt, it is carbonyl CO. Okay, it is a neutral monodentate strong field ligand. Okay, so now tell me what is the oxidation state of nickel and its hybridization and magnetic moment. So just give a try for this complex from your side. Here manganese in plus manganese. Okay, let us write the complex first, -3. Okay, this is a complex is given, pick out the statement, correct statement they are saying. So what is the oxidation state of manganese? First we need to calculate. Okay, so manganese, let us say this is X plus 6 cyanide ligands are there, 6 into each one will be having -1 charge. Overall molecule is having -3 charge. Let us make it like this. Okay, so X value will be -3 plus 6, overall it will be +3. So this is the oxidation state of manganese in the given complex. I hope it is clear up to this point, right? Okay, next finding the oxidation state is a step 1 you have to make. Step 2 is what is the nature of this ligand. So even while identifying whether it is negative or positive or which kind of ligand, or it is zero ligand, I mean neutral ligand, we need to identify now. So we know it is neutral, negatively charged ligand, and now itself we get to know it is strong field ligand, right? So you can make that clarity here. First we need to identify the coordination number, and we need to find the type of ligand, whether it is neutral ligand or charged ligand. So if it is charged ligand, take the charge in the bracket, multiply with the number of ligands given. Okay, and for metal you take it as X, therefore find it its oxidation state. Okay, now after finding the oxidation state, find its nature, whether it is weak field ligand, strong field ligand. So cyanide is a strong field ligand. Up to here it is done, right? The next thing is write the electronic configuration for this metal Mn plus 3. How can we write Mn? 25 atomic number, so you can say 3d5. If it is 25, write 3d5 4s2, so 4s2. So this is the electronic configuration in the neutral form, but here it is plus 3 now, so remove 2 electrons from S and 1 electron from D, therefore we have D4, 3d5 become 3d4. I hope it is clear up to here, right? Now represent them in the orbitals like this. So how many are there? 1 2 3 4. Up to here it is also clear, right? Next, after 4 we have 4p0 also, right? This is the energy orbitals, I mean the orbital, next orbital is 4p after this 4s. I hope it is clear. Next, now how many ligands are there? 6 ligands are there. It means we require 6 empty orbitals are required, right? Now in order to make the 6 empty orbital, we have a strong field ligand and we have 4 s and 4p orbitals also. It means totally how many we required? We required 6 orbitals. Therefore these electrons, if they get paired up like this, so what happens here? We can get see, even one electron is getting paired up. So if this electron is getting paired up, we will be getting something like this. If it is paired like this, okay, 4 electrons are there, Mn plus 3 means, okay. So now how many orbitals we required? We required 6. Why? Because 6 hexadentation now. So 6 ligands are there, so 6 orbitals are required. So these are 4, okay, 4 over, and this is 5th one is also there. By pairing this electron, we got generated one more empty orbital. Therefore, one ligand donates, strong field ligand donates to these 2 orbitals, 1, 2, and the next for this, and the remaining will be for this one. Like this, so 6 ligands are donating pair of electrons to each of these orbitals, right? Okay. So now what are the orbitals utilized here? D2. So it is D2, and the next here it is S, and here P3. So D2 sp3 is a hybridization of this particular complex. Okay. Now is there what D2 sp3? What is the geometry? So geometry will be octahedral. So octahedral. So just go through the options. It is having D2 sp3 hybridized and octahedral, right? So that is the option. So they may give one more option here if you look properly. So fourth option it is mentioned sp3 D2 hybridized with octahedral. Which is correct here? We can go with the first option only. It is D2 sp3, not sp3 D2. So it is D2 sp3 octahedral complex. For both of them have octahedral only, but if inner d orbital is used, so for example 3d orbital is used here, so I can say D2 sp3, that is what the inner orbital complex. Okay. So if the ligand is weak field ligand, if the same case, if we have this one, Mn Cl6 minus 3. So here also Mn plus 3 configuration electron oxidation number. So we will get 3d4 only. But if it is 3d4, we need to fill the electrons like this now. So now here we have only one empty orbital, but we require 2 empty orbital. But pairing is not possible in case of weak field ligand. Chloride ion is a weak field ligand. Therefore pairing will not happen. So we don't have required number of inner d orbitals to make the hybridization for hexacoordinated complex. Therefore it will not use this inner orbital, it will use as outer one. After 4p we have 4d0, so that orbital is utilized. So therefore we can get sp3 d2 hybridization, s from here, p from here, d from 4d, the last one, outermost shell. So I can say outer orbital complex. So whenever we have weak field ligand, we will get outer orbital complex. So magnetic moment of outer orbital complex will be always greater than this inner orbital complex when they have same oxidation state. Okay, I hope it is clear for the same metals with same oxidation state. Okay, so if the metal complex is given this, so fourth option is suitable for this particular option answer. For this particular question, fourth option is correct. For the given question, the second option is correct because it is having D2 sp3 hybridization. Okay. The next thing we will be discussing here is, this question I have given it as a homework for you already, so you can make it. Okay. And I just wanted to give you this question as a work based on the previous discussion. Okay. So I want answer for this question. So just find cyanide is a strong field ligand, water is a weak field ligand, again cyanide, again water. So I told you already, cyanide strong field, water weak field, done. Find the oxidation state. After finding them, find the hybridization state, hybridization of each of this compound. So if you seen any of the unpaired electrons, find the magnetic moment. Just use the formula N equals to number of unpaired electrons you will get from the complexes. Use mu equals to root over N into N plus 2 Bohr magneton. So for this, you can take hashtag question number 3 and write answer for this in the comment box. I will be waiting for you. Okay. And this one, listen here, very important, CFT, crystal field theory. So here we have hexa-coordinated complex. So iron, if you calculate the oxidation state, you will be getting plus 2. So atomic number 26. So it will be 3d6, 4s2 in the atomic form, but plus 2 means remove 2 electrons. we can write like this. So I am writing the orbitals, d orbitals like this. So 6 electrons are there, fill them like this. Yes, done. Then next, so whenever these metal ion is placed in the ligand field, ligand solution, the d orbital degeneracy is getting lifted. It means the energy of d orbitals will be lifted like this. Okay, like this. Now write the electronic configuration as it is. So now I am saying this is the energy profile diagram, let us say. Okay. Now this is in the presence of ligand field. It means metal ions we have kept in the ligand solution, therefore the d orbital degeneracy getting lifted. Now due to the approaching way of ligands, these orbitals will be splits into two different energy levels. Okay. So now here we have different orbitals here. Some orbitals are along the axis like dxy, dyz, dxz, dyz, and some orbitals are in between the axis. These are in between the axis, and this x square, y square, dz square, these are along the axis. Okay. Now these will be splits into two energy level depending upon the approaching way of ligand. Okay. Now when it is in octahedral complex, okay, octahedral complex, ligand approaches towards the axis, therefore the energy of these orbitals which are along the axis getting increased. So these two orbitals, these are what, dx square, y square and dz square energy is raised. Okay. And for d, other three orbitals are what, dxy, dyz, dzx. So these are the three degenerate orbitals, these are the two degenerate orbitals. So this down one will be calling as T2G set and above one will be called as EZ set. So T2G, triply degenerated orbitals. Okay. So now the remaining thing here we need to know. So this neutral center, this midpoint is called Barry center. So this is what, Barry center. Okay. Now here this is what, T2G set, EG set I told you now. So now one more thing here we need to know. They are asking correct electronic configuration of central atom here. So how can we write the correct electronic configuration? Cyanide ion is a weak field ligand or strong field ligand. We know cyanide ion is a very strong field ligand. So whenever we have strong field ligand, the splitting of these orbitals takes place very greater extent. Therefore electrons will be filled in the lower energy first, all the electrons. Once after filling all these orbitals, then only goes to the higher energy. Therefore 6 electrons are there, fill all those things in the down first. Okay, 6 is done. If the 7th is also present, then only that goes to the higher energy. When it happens, whenever we have strong field ligand. Or if weak field ligand is there, then fill the first 1 electron here and also 1 electron here by following Hund's rule. But whenever we have strong field, first fill all the electrons in lower energies first, complete them, fill 2 electrons in each orbital, then only you can go to the higher energy state. That's it. So now what is the electronic configuration here we got? T2G6, EG0. So this will be the option. So T2G6, EG0. So second option is a perfect for this particular question. Okay. I hope it is clear. Now for finding CFSE, we have one more thing. So now this is a Barry center. Let us say here the energy is 0 and below this we will be having negative energy, that is 0.4 delta naught, and above this we will be having energies in positive terms, that is plus 0.6 delta naught, like this we should write. Okay. So now CFSE, crystal field stabilization energy, equals to right, minus 0.4 into number of EG electrons, T2G electrons, okay, plus 0.6 into EG electrons, like this we need to write. Okay. So how many T2G electrons are there? Minus 0.4 into number of T2G electrons are how many? 6, and EG electrons are 0.6 into 0, 0.6 into 0, yeah. So it will be minus 2.4 delta naught. This will be the CFSE value for this question. I hope this is also clear. How to find CFSE value also clear. So if it is weak field ligand, what I told you, fill 1 electron down and also go to the higher energy, just like a free metal, how we will be filling by following Hund's rule, that method you follow. okay, for weak field ligand. If it is strong field, follow this method. So I will be asking you to calculate it for FeCl6 2 minus CFSC value, write it in the comment box. I will be waiting for your answer. Hashtag question number 5, let us see. That will be the homework question. Okay, this I told you already how to do this. Yes. The next thing is, again similar to this, look into this question again, similar to this. Ammonia, see, you remember for copper tetra-coordinated complex, here the hybridization is sp2d. What is the hybridization? sp2d square planar, okay. So one unpaired electrons will be present in that, okay, therefore it is paramagnetic, so d2, okay, d2. And here we will be having NiCN4 minus 2 means we already did. So what we got from that? So all the electrons are paired, we already did. Just check your pages back, go and check your pages back. So there we already did. So it is diamagnetic tetra-coordinated complex with a square planar geometry, okay. And then next in ethylene diamine, so it is bidentate ligand, so EDTA hexadentate ligand, that's it. So choose the option R4, 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 only these two options, S3, S3, both options. Next P2, P2, only third option is there, yes, third option you can choose. I hope it is clear how we are doing. Okay, done. So this is about the class. I hope you are enjoyed the session, and I hope this will be definitely helpful for your preparation. So if you really like the content, please click on the like button and share with your friends. Thank you for watching.